Yes, ma'am. Uh, Hello, everyone. We are here to present our PBL project titled Plant Disease Detection using DL. Our team has four members. I'm Apeksha here, Priya Amchikeri, Rakshita Rudramani, and Rakshita Dabadi. Together, we have worked on designing, developing, and testing a deep learning model that can efficiently detect plant disease from leaf images. In agriculture, detecting diseases early is very important because if a disease spreads, it can damage a large part of a crop and cause big financial losses for farmers. And right now, farmers usually rely on looking at plants themselves or asking experts to identify diseases, but this is slow, costly, and sometimes inaccurate, especially when there are many plants to check. To solve this problem, we developed an AI based system that can automatically look at an image of a leaf and tell whether the plant is healthy or diseased. It can also identify the specific type of diseases like leaf blight, rust, and mildew. This method is faster, cheaper, and easy to use through a mobile or a web application, helping farmers detect problems early and take action to improve crop yield and income. In this slide introduction, plant diseases are a big challenge in agriculture because they can reduce crop yield and cause serious financial losses. Traditionally, identifying these diseases depending on experts like agriculturing officers or plant pathologists, but this process is slow, expensive, and sometimes accurate because it depends on visual inception, which can vary from person to person. With AI and DL, we can make this process much easier using DL models, especially CNN. We can detect plant disease just by analyzing leaf images. This approach is faster, cheaper, and more reliable, giving farmers a practical solution. In the next slide, problem identification. Farmers often have trouble detecting disease early and accurately. Manual inception is time consuming and costly, and delays let disease spread and reduce yield and income. The main problem is that there is no automated system to detect plant diseases quickly and accurately. Our project solves this by creating a reliable AI-based detection system. In the next slide, literature survey. Um, Many studies have tried using DL for plant disease detection. For example, Mohanty ETAL in 2026 used CNN and got high accuracy, but only in lab conditions. In and Fahrenheit tons in 2018 also got a good result, but there was no real time or mobile application. Saljo Zevic ETAL in 2016 faced data set limitations affecting performance. From these studies, we saw the gap. Most models work in a labs, but not practically in real farms. Our project focuses on filming this gap by building a practical, real-time, and field-ready solution to detect plant disease efficiently. Next slide will be continued by Rakshita.
Hello, good morning, good afternoon, ma'am. I am here to explain about objectives. The main goal of our project is to build an AI-based system that can automatically detect plant leaf disease accurately and in less time. In traditional farming methods, disease identification is mostly manual, which is slow, requires experts, and sometimes leads to wrong decision. Our system solves this problem using machine learning and image processing. Our key objective is detecting plant disease at an early stage to avoid major crop loss, using deep learning, especially CNN, to improve detection accuracy, providing a fast and automated solution for farmers. reduces dependency on experts and manual inspection, making the system simple, user friendly, and cost effective. So, we aim to bring AI into agriculture to support farmers and improve productivity. Next, requirement specification. Uh, there are three types of requirement specification: functional requirements, non-functional requirements, and data sets. Let's discuss about functional requirements. It describes the core features on the operation that our system must perform. In our project, the functional requirements are: the system should accept the leaf image as an input. User must be able to upload images from phone, laptop, or camera. The system must process the input image. This include resizing, noisy, removal, and normalization. The system should analyze the image using a trained CNN model. The model extracts features and classifies the disease. The system must identify and displays the disease name. The system should show the prediction result with accurate percentage. Example percentage is perform 93%. The system must allow our user interaction through the simple interface built using Flask, so it is user friendly. The system should give fast result after uploading the images. Functional requirement decide what the system does: input, process, predict, and output. Let's non-functional requirements. Non-functional requirements focus on the performance, quality, usability of the system, not specific function. Accuracy. The model should give high and reliable prediction accuracy. Our model achieves 95% performance response time. The system should predict the disease within a few seconds after an image upload. User friendly. The interface must be simple so even farmers without knowledge can use it easily. Scalability. The system should support more crops and disease in the future. Reliability. It should give correct prediction even when the tested multiple times. Portability. The model should run on laptop, mobile, tablet, or phone. Yeah, other. Next methodology. Our project workflow has the following stages: data set collection, collect leaf image, LP plus diseased, use the real world sample. Data pre-processing, resize images for uniform input, remove noisy and unwanted distraction, normalize pixel values for better model learning. Data augmentation, apply rotation, zoom, flopping, brightness changes. Helps increases data set size and reduces overfitting. Make model more accurate in real life conditions. Train test split. 80% of data used to model training, 20% of data used to testing and evaluation. Model building using CNN. CNN extract important features automatically from the images. Best model for the image classification takes. Model training. We train the model using TensorFlow. Multiple echoes are used to improve learning. Prediction system. User uploads leaf image, model analyze and predict the disease name, result evaluation, check accuracy and performance metrics, ensure model is reliable and efficient. Our system flow is input leaf image, pre-processing, CNN model, training, disease prediction, and output. By following this structured methodology, we can ensure that our model gives accurate result, work efficiently, and can be used in real time and real world agriculture condition. Next, continued by Rakshita Vidabadi.
Rakshita, Rakshita the body. Start the session.
The present.
Priya, unmute and talk.
Hello everyone. Today I'm here to explain the next steps of my projects, which is the plant disease detections. In the steps, I will covering the main four parts like an system designs, architecture, models, and the tools can be used in this projects. First, the system designs. The system designs means how the entire project is be planned and how the data will be workflow from the input to the output. In our systems, the main goal to be detected whether the plant leaf is be the healthy or be diseased. If the diseased, which type of any disease it is. First, the user can be upload or be capture the plant leaf images through our systems. Then the image goes through the several steps: pre-processing, feature, extractions, model predictions, and the finally the displaying the results of any users. For example, when a farmer can be take the pictures of an leaf, the system can be processes. It will be the whether the healthy or be the affected the diseases like an a leaf can be spocked or be the rust. Next, architecture. In the architecture, next it means that the structural designs how the different components are be connected and work together. First, our architectures is be mainly included under these steps: the user interface where can be uploaded the images, and the pre-processing unit where the image can be cleaned and be resized, the models and be the interface engines which can be the predicted the diseases, and the database which can be stores the images and be predicted the results. Then the output models which can be shows the results can be the confidential levels to the users. We can be imagine the architectures like an a pipeline. The image can be entered from the one end, that can be processed through the different processing stages, and they can be come out from the another end with a clear result. Our architectures can be followed by the client servers models also, where the front end can be collected the input and the back end can be perform the model processings and be the results for the predictions. Next, model. In this model, uh, which can be the most important part of our systems. The models can be trained by the machine learning or the deep learning algorithm that can be clarify the plant leaf in the different diseases categories. We can be explain the model by using the large data sets of an plant leaf images for the both disease or the healthy one. First, we pre-processing the all the images and the resizing, noisy removal and the normalizations. Then we can be trained the models by using the CNN because the CNN is a very effective in the image recognition task. The models can be learned to identify the patterns, texture and the colors that can be represented the different diseases. And these models has been used the project like a model net v2 in the lightweight of an efficiency in the deep learning. Since the model net v2 is be the pre-trained, it can be helps to achieve the high accuracy even than the smaller data sets when it can be fast and the suitable for the real-time plant diseases detections. Next tool used in our plant diseases detection projects, we are use the tools technologies that can be helps us to build and be train the model efficiently. We use the Python for the main programming languages because it can be the simple and be the supportive powerful machine learning libraries. For the deep learning we can be use the TensorFlow and the KRS framework. These tools helps us to the designs and we train our CNN easily and efficiently. The sometimes we can also use the PyTorch, which can be the another deep learning framework. It is used for the model experiment. Our data sets can be taken from the plant diseases data set that can be contain the label images or the healthy and be the diseases leaves. We can be selected the tools because the CNN is be based by the build of an tensor flow and the KRS. They can be perform the better traditional ML which can be the CNN or be the KNN in the image recognition task that can be give up the 98% of accuracy that can be reaches to the studies. Overall, the tool make the model accurate, reliable and be the faster for the real plant diseases detection. Justification. We can be choose the tools because the CNN model too can be built by using the TensorFlow and be the caser performs which can be better in the traditional machine learning models like NSCVM or KNN for the image recognition task that can be provide the high accuracy even up to the 98%. So research can paper for the plant disease detections and also the tools like Anacaser makes the model building and be the training for the simpler and the faster which can be saves a lot of time during the development. Next slide will be continued by Priya.
I am Priya. I am here to explain the implementation overview. Let's move on the implementation parts. I trained the model on labeled images of plant leaves and it achieved more than 97% accuracy in predicting the plant disease. Now let me explain step-by-step process I followed for implementation. Data uploading and extraction. I started with the dataset containing the labeled images of the plant leaves. The dataset was uploaded as a zip file extracted and organized into the training, validation, and testing folders. These structures help the model learn effectively and also evaluate the performance probably. Data pre-processing. Next, I pre-process the images, basically preparing them before training. This includes recycling the images pixel values and performing the data augmentation like rotation, flipping, and zooming using an image data generator. This helps prevent overfitting and makes the model more general and robust. Next, model building. For the model building, I use MobileNet V2, which is a type of transform learning module. Transform learning means using pre-trained model that already knows how to identify basic images, features, and then fine tuning it for our specific task. In this case, plant decision classification. Training. The model was trained for 25 times, meaning it went through the entire dataset 25 times. Initially, the accuracy was around 37%, but after training, it improved to the 97%. The validation accuracy, which checks performance as unseen data, reached up to the 100%. This shows that the model learned very well to distinguish between the diseases categories. Next, last evaluation. Finally, I evaluated the model and found that it achieved high accuracy, low loss, and executes smoothly without any runtime errors. Next, code explanation. Can't take a
Which tool you are using for your code?
In this code, this will set up all the tools we need or load our data set and upgrade, train and test our plant disease detection model. First, we update TensorFlow to latest
Which
version.
tool you are using for your code and all?
what one?
Sorry?
Which tool you are using for your code?
Python,
TF Keras, TensorFlow.
Sorry?
Google Colab.
Python, TensorFlow, Keras.
It is developed by you or you are extracting it from Chrome or somewhere?
Ma'am, both.
Yes, ma'am. We only
Sorry?
executed this.
You executed this code, right? Okay, continue.
Um, we install extra tools, TF Keras to build a DL models, TensorFlow Decision Forest for tree-based models, and TensorFlow Text for text processing. We also use the image data generator to prepare and change images in different ways, which helps our model learn better. Then we import a TensorFlow to build models and image data generator and Keras tools to create and load models. We also use a Matplot LIB to make graphs, NumPy to handle data, and PIL to open and process images, and OS and zip file to manage files, and finally we print the TensorFlow version to make sure it is installed. Next, we uploaded our dataset into Google Colab. We use the files module to upload files. Files.upload upload opens a box so we can select our dataset zip file. We use os.listdir function to check that the file is uploaded, and we use its path in a zip path so we can use it later. After uploading, we extract the data set. we set the zip file path and folder where we want to extract it. uh, Using zip file, we safely open the zip and extract all the files. Finally, we print the message to confirm the dataset is ready to for training and validation. Finally, we check the dataset structure. We go through the folders to see the main folder, subfolders, and some example files. Then we define a base path has the main folder with all the plant images and the list all the categories or classes. We also set the paths for training and validation data, which we will use later for a model training. Next code will be continued by Rakshita.
Import libraries from TensorFlow cursor preprocessing image. Import image data generator. This line imports image data generator, which helps to load, preprocess, and argument images like flipping, zooming, etc. to make the model learn better and avoid overfitting. Setting the base directory. This is the path to the main folder that contains all the subfolder. Each subfolder represents a disease class, for example, healthy, disease, exam, etc. Image and batch settings. Image size is equal to 128, 128. Every image is resized to 128 into 128 pixel, and the model will process images in batches of 32 at a time. Image data generated for the augmentation. This step pre-process the argument the dataset. Rescale is equal to 1 dot slash 255. Normalize pixel values from 0 to 225 to 0 to 1 for the faster training. Validation split is equal to zero point 0.2. Split dataset 80% training, 20% validation. Rotation range, width, shift range, etc. Randomly transfer image, rotate, zoom, flip, etc. to make the model more robust and generalized better. Create a training and validation sets. Loads the training images from the folder, resize them into 128 into 128, groups them in the batches of 32, and labels them as a multi-class. Uh, this loads the validation images 20% of total datasets used to check the model's performance after each training steps. Importing MobileNet V2 and required models. MobileNet V2, a pre-trained lightweight CNN model trained on ImageNet layers models to build our custom model. Load the pre-trained model. Here, ModelNet V2 is loaded with the pre-trained weights from the ImageNet, a large image dataset. Include top is equal to false. Removes the final classification layers. Trainable is equal to fail. Freezes the base model so only our new layers will train. This helps use transfer learning efficiently. Adding custom layer. This creates a new neural network using ModelNet V2 as a base. Global average pooling 2D. Reduces each feature map as a single number. Reduces complexity. Dense 256 activation is equal to reload. Adds 256 neurons to learn specific features of the disease. Dropout 0.3. Randomly drop 30% of neurons to prevent overfitting. Compile the model. Defines how the model will learn. Optimizer with a small learning rate 0.001. Loss function categorically cross used to multi-class classification. Matrix accuracy to measure performance. Model summary displays all layers, output, shapes, and the number of trainable parameters. Example out. The model has about 2.5 million parameters, most from the pre-trained model net V2. We used a pre-trained model net V2 model for the plant disease classification. First, we pre-processed and augmented the datasets using image data generator divided into 80% of training and 20% of validation. The Model V2 base model was the loaded with ImageNet, weight, and frozen to reuse its larger features. Then we add custom layers for the classification and compiled the model using Adam Optimizer and Categorical. Finally, we viewed the model summary showing all layers and parameters. Next continued by Priya M. Chikeri.
Train the MobileNet module. Mobile.fit starts training the module. Next, provides training images with labels. Approach 25. Model learns over 25 complete cycles. Validation underscore data. Test the performance after each lifetime to check the generation. Here is the model started with 37% accuracy, which is the normal, and after training it's reached to the 83, above the 75%. The loss also dropped from 1.57 to 0.14, confirming strong learning. Overall, our module achieves for more than target of 70% accuracy. Next, import Matplotlib. It imports the Matplotlib, a Python library used to create a graphs and visualization. We use it to collect accuracy and loss over the training approach, so we can visually understand how our module learns. Next, training and validation loss. A new figure of the size 8 cross 5 inches is created for the clear visualization. PLT.plot draws two lines, one for training accuracy and other for the validation accuracy. The title and the access labels describe the chart. PLT.legend shows the labels, training and validation to identify each line. PLT.grid adds the grid lines to make the graph easier to read. Final PLT.show displays the plot. This graph shows the model's accuracy increases with each approach. If both lines go up and stay close together, it means the model is learning well and generalized correctly. Similarly to the previous graph, but this one is shows loss, which means how much error the model is making. Measuring how will the model fits training data. Shows the performance of the unseen data. Our training contains both losses to decreases, showing that the model is learning effectively. This helps us the confirming that model is not overfitting or underfitting. Smoothly decreasing the loss curves means the model is performing correctly. Blue line indicates that training accuracy and validation accuracy. In this, blue line indicates that training loss and validation loss. A blue line increases steadily with the approach. The orange line also rises and stabilizes near 0.95 to 1 or 95 to 100%. The orange line validation accuracy also rises. This means the model is learning well and generalized, probably no sure overfitting is visual. In this, both training and loss validation decreases constantaneously as the approach increases. The line are closely together, showing good convergence and balanced training. Lower final loss values mean your model predict as becoming more accurate. Next will be continued by Rachita.
Load library. First, we import the required library, like example like in a NumPy for the array tensor.flow.ksr.model.load model. If the model can be trained, the model and be image can be handled. Load and this save the model files. First, the model can be trained the model from the disk by using the load model by the context dot plant diseases models underscore the model net. This can be stored the extracted networks and the wait for the trained earlier. Get the classes of an label using during the training. I can be obtained, but the class can be the label from the training generators and it can be converted them to the list and the print them. Then it can be labeled the map numerical outputs back to the diseases names. Choose the simple test images. For the demonstration, I can be pick the images from the class folder. For example, the file inside the chosen classes so we can get the test of an a model on the real sample of an a database. Then the pre-processing the images can be extracted during the training. First, the images with an a pre that can be converts that can be converted the RGB by the resizes it into the 128 into the 128. The size can be the shape will be used in the training that can be converted into the numpy of an arrays. Then the scales can be the pixels of an values 1 bar to 55. It can be explained the dimensions so the model can be accepted the batches of an one images. Run the model can be predicted. I call the models can be predicted the image arrays which can be turned the probability for the each classes. Then they get be the index of an highest probability by using the np dot array next to find the predictor the class. The map index by the back of an human reliable label of an print by using the label map. The step 3 I can be print the predicted diseases names. For example, the printed output like an a tomato, the tomato yellow leaf, the curly virus. First, we can be use the cursor warning by the complete of an a compile the matrices aren't be built when they are be loading. It is be the normal when the loadings is be the safe for the models by only for the interfaces. It doesn't not affect the predictions. And finally, the conclusion of this code is be the pipeline of an load that can be trained the model net based the model, the pre-processing of an input leaf images identified to be trained, the predicted the diseases classes and the output the diseases name. The model can be reliable of an classifies the plant leaf conditions for the each test images that can be predicted. For example, the tomato underscore the yellow leaf underscore the curls of an virus. Next will be continued by Priya.
Next results we seen in the code. Final accuracy is 97%. Validation accuracy up to 100%. Loss reduction from 1.7557 to 0.14. These numbers clearly show that the model learned effectively. The drop in loss indicates the model's prediction become more precious and confident. Next conclusion. To conclude, this plant is training and validation. The model achieves very high accuracy, above 97%, showing its efficiency and reliability. The system can help farmers detect plant disease early so they can take timely actions to protect crops and improve the yield. This project also demonstrates the power of transform learning, how pre-trained model can be adapted from the
Priya, your PPT is not visible. PPT or whether it is code or PPT, it is not visible.
PPT. Ma'am.
Okay. Is it visible to everyone?
Yes, ma'am, it's visible.
Oh, it's not visible for me. It's okay, continue. Priya, continue.
Yes, ma'am. Mohit, ma'am.
Done, everyone?
Yes, ma'am. Completed.
Completed?
Yes, ma'am.
Which algorithm or model you are using in your project?
CNN, ma'am.
CNN. What is CNN?
Convolutional neural network. It complete
What is the purpose of using CNN?
It takes the automatically fixes, ma'am.
Sorry?
And it is the type of deep learning model that
Hmm.
works especially well with images.
Okay. What are the libraries you have imported for your project?
Python, TensorFlow, and the yes,
Only two libraries?
Python.
Then what are those?
Ma'am, it's not audible.
Sorry? Am I audible?
Yes, ma'am.
Yeah. What are all the libraries you have imported?
TensorFlow gets a pre-processed customer two libraries imported.
Hmm. In your project, what kind of image you are taking? Whether it is leaf, stem, or root, or whole plant?
Leaf, ma'am.
Leap, ma'am.
Leaf. Okay. How the images are labeled before? Whether it is showing what kind of disease it is, how it will be labeled. Got my question?
How the images are labeled.
Hmm.
Folder create muddy images.
How the diseases will be labeled? It will be in image classification, right?
This
Yeah.
has
Ma'am,
How
been
they are labeled?
images are not labeled manually inside the code. checker automatically labels the image based on the photo.
Okay. You have implemented web app or mobile app in your project. How
Uh,
the
Now,
user can
application, ma'am.
upload the image through web or app?
website, ma'am.
Through web. Then what are the tools you have used for your front end?
NumPy for
Sorry,
for
for your
handling
website, which tools
TensorFlow
you
and
are
Keras,
using?
Matplot,
Now,
LIV.
No,
ma'am,
for
in this
website.
HTML to structure on a web page, CSS for styling, color, layout for design, JavaScript in backend, Flask and Python for
Hmm.
framework, TensorFlow and Cursor, open tool to express Streamlit Flask server.
How many images are there in your dataset?
Ma'am, around 100.
One second.
We have divided it like separately, three classes. In first class, like 75 images. In second class, 15 images and 10 images in third class. We created in that in subfolder.
Okay. Which dataset you are using?
Uh, village,
Sorry.
plant village, ma'am.
Okay. Okay. Thank you. Everyone can leave.
Thank you, ma'am.
Mm.